Finding a single global optimum is difficult. Finding every significant mode in a high-dimensional, black box landscape is a computational nightmare. And yet, for Bayesian model averaging, mixture fitting, and robust scientific inference, you literally cannot proceed without cataloging the full mode structure. The problem is architectural. Classical optimizers like basin-hopping, CMA-ES, and multi-start gradient descent are fundamentally sequential or population collapse prone. They were designed for CPUs, not for the thousands of parallel arithmetic units sitting on your GPU. Today, we're breaking down ChiSao, a GPU-native population optimizer that doesn't just find modes, it maps them. It does this through a deliberate convergence-anticonvergence oscillation cycle, achieving 100% mode recovery across 42 benchmark functions up to 64 dimensions, while running up to 39 times faster than CPU baselines. Let's look under the hood. Multimodal optimization asks a straightforward question. Given a function of d dimensions, accessible only through black box evaluations, where are all the local maxima? The catch is the scale and the hardware mismatch. On a modern GPU with over 10,000 CUDA cores, evaluating a batch of samples takes roughly the same wall clock time as evaluating a single point. Sequential methods waste this capacity entirely. Population methods like CMA-ES or particle swarm optimization use parallelism only within a single generation step, and they almost always suffer from mode collapse, converging the entire swarm to one basin and losing everything else. Multi-start gradient descent is embarrassingly parallel, but it's dumbly parallel. Each trajectory finds at most one mode, and once they converge, you're left with duplicates and wasted computation. ChiSao changes the architecture. It treats the entire population as a single batch, running simultaneously across the GPU, and introduces a structural asymmetry that standard optimizers simply don't have. At its core, ChiSao runs a fixed sequence of 6 phases, repeated across a few oscillation cycles. The ordering isn't arbitrary. It's engineered to maximize exploration while preserving confirmed modes. Phase 1 is convergence. Every sample in the population runs a batched L-BFGS pass toward local maxima. Because this is vectorized across the GPU, thousands of samples optimize simultaneously. Phase 2 is stick detection. Once convergence finishes, ChiSao checks 2 conditions. The gradient norm must be near 0, and the function value must exceed a quality threshold relative to the current best. Samples passing both are marked as stuck. Here's the key asymmetry. Stuck samples are frozen from further exploration, but they continue to participate in peak refinement. The rest of the population keeps moving. Phase 3 is deduplication. Using an L-infinity metric, ChiSao removes spatially overlapping confirmed peaks, keeping only the highest quality one and preserving its inverse Hessian for width estimation. This step is non-negotiable. Disabling it causes immediate mode collapse, because the receding phase would otherwise replenish consumed slots from known peaks without removing them, saturating the population at a single mode. Now if the population is running low on unfrozen samples, ChiSao recedes. It uses 2 complementary strategies. When many samples are still exploring, it fires Repulse Monkey, shooting random rays from unfrozen points to disperse new candidates away from known peaks. When the population is nearly exhausted, it switches to Golden Rooster, generating orthonormal ray directions via QR decomposition from confirmed peaks to systematically probe orthogonal basins. This receding feeds directly into Phase 5, hands like clouds. Here, unfrozen samples ascend using a stochastically smoothed gradient. By convolving the gradient estimate with a Gaussian kernel at a scale derived from the population spread, ChiSao blurs out subscale noise and local ripples, exposing the global basin geometry. This isn't simulated annealing or random perturbation. It's directed motion on a smoothed landscape. Phase 6 is anticonvergence. Unfrozen samples take momentum-based gradient descent steps. The momentum term carries them across valleys into new basins. This deliberate escape mechanism is what keeps the population from stagnating in secondary traps. On the final oscillation cycle, exploration phases are skipped, allowing the last convergence pass to output clean, unperturbed peaks. Let's talk hardware. Every operation in ChiSao vectorizes over the sample index. For a population of size n and dimension d, the wall clock cost per oscillation cycle scales with a batch size divided by the number of GPU cores. In the GPU-saturated regime, where n times d is less than the core count, the wall clock time becomes effectively constant, independent of both population size and dimension. This is the GPU dividend. On a function like the rotated hyperellipsoid at 64 dimensions, ChiSao runs in roughly 50 seconds, while basin-hopping takes nearly 20 minutes. That's a 39 times speedup, and it's purely from batch parallelism. Even under derivative-free evaluation, where gradients are computed via finite differences, which is the absolute worst-case scenario, ChiSao maintains this efficiency. The algorithm only requires batched function and gradient evaluations, making it a drop-in exploration module for any downstream optimizer. The benchmarks tell the story. Across all 42 functions in the Simon Fraser University optimization suite, spanning scalable multimodal, bowl, valley, and fixed low-dimensional landscapes, ChiSao achieves 100% mode recovery up to 64 dimensions. CPU baselines like differential evolution, basin hopping, and CMA-ES collapse entirely at dimensions 8 and above on the hardest multimodal functions. On rastrogen and Levy at high dimensions, ChiSao maintains perfect recovery while baselines fail completely, yet still run faster. The seeding strategy matters. For Ackley, which has a nearly flat outer region, uniform random seeding collapses at dimension 8. But the structured Carey-Tiger seeding, which casts rays from domain vertices and edges, cuts directly through the flat region and maintains 100% recovery. Noise robustness is where ChiSao really shines. When the objective function is corrupted by additive Gaussian noise up to a standard deviation equal to the signal scale itself, mode detection remains 100% reliable. This isn't luck. The convergence-anticonvergence cycle drives trajectory-averaged gradient estimates, which absorb per-evaluation noise that point-evaluation methods simply cannot tolerate. Zero spurious detections up to a noise level of 0.5. Ablation studies confirm the architecture. Removing deduplication causes catastrophic failure across all dimensions and functions. Removing anticonvergence improves performance on one deceptive function at low dimensions, but destroys recovery on Levy at scale, proving that momentum-based escape is necessary for high-dimensional basin crossing. The algorithm is robust to hyperparameter sweeps, with only the anticonvergent step count showing a hard ceiling. Doubling it overdisperses samples past narrow basins, causing the next L-BFGS pass to return from outside the basin of attraction. The default setting sits safely on the safe side of this ceiling. No optimizer is perfect. ChiSao assumes a smooth objective. It estimates gradients via finite differences or accepts them analytically, so discrete or non-differentiable problems are out of scope. The quality gate threshold, which filters out modes below a log decade of the global maximum, is the primary source of failure. On deceptive landscapes like Schwefel or narrow ridges like Buchan N6, converged samples fail the gradient norm or likelihood tests, and the quality gate rejects them. Baselines without quality gates succeed there, but they pay for it with spurious peak detection on harder multimodal problems. Additionally, ChiSao's deduplication and receding logic does not scale to exponentially many equal-height modes. The theoretical analysis currently covers log-concave convergence guarantees and first-pass coverage bounds. A full Markov chain analysis of basin crossing probability under the anticonvergence momentum dynamics remains an open problem. But empirically, the oscillation cycle consistently outperforms sequential and collapsing population methods. ChiSao represents a shift in how we think about black box multimodal optimization. By treating exploration and convergence as a deliberate oscillation cycle, freezing confirmed modes, and exploiting full GPU batch parallelism, it solves a problem that has stubbornly resisted scaling. It's available as an open-source Python package on PyPy, with full benchmark scripts and analysis code on GitHub. If you're working in Bayesian inference, scientific computing, or robust machine learning, where cataloging the full mode structure is non-negotiable, it's worth dropping into your pipeline. The future of optimization isn't just about finding the peak. It's about mapping the entire landscape and doing it at the speed of modern hardware.